Okay, next up we are going to develop a couple of formulas that involve factorials that allow us to count up the number of elements in particular sets. So I want to start with just an example. Suppose we have a certain committee that has 5 members in the committee. Those 5 members are named Al, Bob, Carol, Denise, and Ed. The committee needs to elect a president, a vice president, and a treasurer. The question is, how many ways can this be done? Now, a question phrased like that is going to become very common in this discussion. How many ways can something be done? And that phrasing can be a little misleading. On its face, when we say how many ways can this be done, you could say, well, we could hold an election, we could pick the people at random, we could hold a contest and see who can run the fastest. They get to be president. There are different methods of choosing the people, but that's not what we mean here. What we mean is basically how many different, and I want to be careful, it's tempting to use the word combination, but truthfully what we're talking about is what's called a permutation. So how many different permutations of these committee members are there if we're choosing 3 of them to fill these 3 positions, president, vice president, and treasurer? So for starters, just to give some examples of what our selections might look like, we could let Bob be president, Carol be vice president, and then Ed be treasurer. So BCE for Bob being president, Carol being president, Ed being treasurer. This would be one selection. Or Carol is president, Denise is vice president, and Al is treasurer, CDA. Or Al is president, Bob is vice president, and Carol is treasurer, ABC. When we say how many ways can this be done, we're asking how many different options like this can we find for a president, vice president, and treasurer. So I just want to point out the wording there. Again, this isn't asking about how many different methods of election could we think of. It's asking how many different outcomes are there when we select a president, vice president, and a treasurer. So let's get down to calculating that. And the way we want to think about that, let me replace my Y really quick. All right, so the way we want to think about that is when we look at this committee of 5 members and we want to choose a president, there are 5 different choices for a president. We could choose Al, Bob, Carol, Denise, or Ed. So there are 5 choices for who is president. Now when we go to choose a vice president, the same person can't be both president and vice president, so that leaves only 4 remaining choices for who is going to be vice president. Okay, one of the people is removed from the pool because they already have a position as president. Then we want to choose our treasurer, and now there are only 3 people remaining in the pool because one person has already been elected president and one person has already been elected vice president. And this is it. So we have 5 choices for president, 4 choices for vice president, and 3 choices for treasurer. And this tells us how many different choices we have all together for our committee of president, vice president, and treasurer. And again, that's what is meant by the question, how many ways can this be done? So 5 times 4 is 20, 20 times 3 is 60, and so there are 60 different possibilities for a president, vice president, and treasurer chosen from this group of Al, Bob, Carol, Denise, and Ed. Now notice this 5 times 4 times 3, that's kind of a factorial, but there are some pieces missing. 5 factorial would be 5 times 4 times 3 times 2 times 1. So we have 5 factorial, but we don't have those last couple of factors. And that should lead us to expect that perhaps there's a formula to do this that relates to factorials. So first of all, we want to define, this isn't an exercise, this is a definition. We want to define that word permutation I mentioned earlier, which each one of those selections of a president, vice president, and treasurer, we call a permutation of 3 objects chosen from a set of 5. In general, an ordered selection of our objects from a set of n total objects is called a permutation. And very important word here is the ordered part of this. So it's an ordered selection. So what I mean by ordered for that particular example, what we were doing was we were choosing a president first, and a vice president second, and a treasurer third. If we were just maybe selecting people for some sort of subcommittee or something like that, and it doesn't matter, they don't have different positions between them in that subcommittee, so the order that we select people doesn't matter, that's going to be something a little bit different. But if the order that we choose the objects matters, we call this a permutation. So we're selecting R from a group of n total. So in the previous example, there were 5 people total, and we were selecting 3. So n would be 5 and R would be 3. Our notation for this is we write npr for a permutation of R objects chosen from a group of n, or another way you may sometimes see it written is P of nr in parentheses. So to relate that to our previous example, again, we had 5 people total, and we wanted to choose 3 of them, and the order mattered. Okay, so if we move down a little bit, I have this property here. This is our formula for how this is calculated. This is given by n factorial over n minus r factorial. And this gives us the number of permutations of R objects chosen from a group of n. So for the previous example where n was 5 and r was 3, we would have 5 factorial over 5 minus 3 factorial. So that's 5 factorial over 2 factorial. So 5 factorial we would break down as 5 times 4 times 3 times 2 factorial. And again, I'm going to stop there so that it cancels the 2 factorial in the denominator. And we're left with 5 times 4 times 3, which is exactly how we worked out the 60 different options for president, vice president, and treasurer. So I said that 5 times 4 times 3 looked like a factorial where we were cutting off, a couple of the factors at the end. Basically, we find the difference between R and N. This represents how many of the people in the committee in this example weren't filling any position at all. And that factorial has to be divided out from the total number of combinations if we were selecting all 5 people for a position. Okay, so let's look at a couple other examples of calculating numbers of permutations. So suppose that earlier committee, again, Al, Bob, Carol, Denise, and Ed, they only need to select a president and a treasurer. So suppose they didn't need to select a vice president. The question is now, how many ways can this be done? So again, this is going to be a permutation, and n in this case is still 5. There's still 5 people in the committee total. But now R is only going to be 2, because now we're only choosing 2 of them. So we have NPR, which is going to be 5 factorial over 5 minus 2 factorial. Again, our formula is n factorial over n minus r factorial, so we'd have 5 factorial over 5 minus 2 factorial. So this is 5 factorial over 3 factorial, which is 5 times 4 times 3 factorial over 3 factorial. And the 3 factorials cancel, and we're left with 5 times 4, which is 20. Okay, let's look at another example, this one a bit longer. Suppose we have a certain bowling league has 32 participants. And at the end of the league, the top 8 players are seeded, and in other words, put in order 1 through 8, and participate in a playoff tournament. So we would say the top player in the league, he's the first seed, the second best player in the league, they're the second seed, and so on and so forth, down to the 8th best player, they would be the 8th seed. So we have seeded the top 8 players, seeds 1 through 8. The question is, how many possible seeds are there? So this is again a permutation question. We want to know how many ways we can select 8 players from the total 32 participants and seed them into the top 8 players. We're putting them in an order. First player comes first, second player comes second, third best comes third, and so on and so forth. So this is again a permutation where we have a collection of 32 objects and we want to select 8. So from our formula, this is n factorial, so 32 factorial, over n minus r, so 32 minus 8 factorial. So that would be 32 factorial over 32 minus 8 would be 24 factorial. So when we go to simplify this, we want to break the 32 factorial down until we reach 24 factorial so that we can cancel those factors. So 32 times 31 times 30 times 29 times 28 times 27 times 26 times 25 times 24 factorial over 24 factorial. The 24 factorials cancel, and we're left with just 32 times 31 times 30 times 29 times 28 times 27 times 26 times 25. Now, thinking back to the original example, another way of approaching this problem would just say, well, there are 32 players in the league, so there are 32 choices for the first seed, which leaves 31 choices for the second seed, which leaves 30 for the third seed, which leaves 29 for the fourth, and so on and so forth. Now, I don't expect anyone to do 32 times 31 all the way down to 25 in their heads, so let's turn to a calculator. We need 32 times 31 times 30 times 29 times 28 times 27 times 26 times 25. Whoops, we missed a 26 here. And this gives us about 4.24 times 10 to the 11th power. So that's big. So we're moving the decimal point to the right 11 times. What do we have? 3, 6, 7, 8 digits here, and then 3 more zeros. So I'm going to go ahead and write this as approximately 4.24 times 10 to the 11th. So keep in mind that's 4, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. So about 424 billion different options. Again, roughly that's approximated because I cut off the 97856 that we had towards the end there, but approximately 424 billion different options. So we see from this example that things like permutations grow very, very quickly. Factorials in general grow very, very quickly. And again, this was listing all the possible seeds there were. So this is how many possible ways there are to have 8 players from this group of 32 then be ordered from 1 through 8.